Hi, kids. All right, we're gonna do some instructional videos about circuits here. So circuits, let's make sure you guys understand some of the basics about circuits. You need to understand what voltage is. Remember, voltage is potential difference, or electric potential. Remember that a volt really is a joule per coulomb. Okay. Remember current. What is current? Current is the flow of charge. Which is really charge, which is coulombs per second. Okay. So if we talk about an amp is really a coulomb per second. Remember, this formula is on your formula sheet. Okay. And really what it's saying is, hey, the current, amps, is the rate of charge per time. So it's how much charge is going by a certain point in a certain amount of time. And then we have resistance. Remember, the units for resistance is an ohm. Remember, what is it resisting? It's resisting current. So if you remember, you can't have current without having a potential difference. And then the amount of current is really dependent on this as well. So if we had a circuit, for example, real basic circuit like this. Okay. Remember how the charges actually move. First of all, the charges are already in the wires and the resistor. Okay. Those are supposed to represent all the little charges. But remember, the charges are already there. All the battery does, or your power supply does, is supply energy to move the charges that are already in the wires. How fast those charges move, which is really the current, this charge per time, which is really the current, is dependent on the potential difference, but it also depends on the resistance in your circuit. So remember, a common misconception is people think, oh, charge goes really fast until it hits the resistor and then it slows down. That's not the case. The resistance in this particular circuit, this resistance would determine the current everywhere in the circuit, okay? Along with that, so that hopefully that makes sense. If you were to do a lab where you graphed V versus I, you would find, if you changed V and you graph this, you'd get this, and you would find the slope of this would equal R. In reality, your independent variable would be V, your dependent variable would be I, which means your slope actually would be 1 over the resistance, which gives you your Vernas equation. So we have V equals IR because it's Vernas. But if you look on the equation sheet, it's actually written like this. The reason that it's written like this is they're telling you, hey, I depends on the potential difference and how much resistance you have. So that's what it depends on. Other basic stuff. Let's see. Oh, you need to understand power. Power. Remember, power is the rate that energy is converted. Well, if you look, do we have energy up here? Oh yeah, we do. We have joules. This is a joule per coulomb. Oh, so if I want joules per second, I have to multiply this by this, which is going to be I times delta V. And if you look, coulombs per second, joules per coulomb, so then I'd end up with joules per second, which is power. What are the units for power? They are watts. What? They are watts. And yes, this formula is on your formula sheet like that. Okay, so just make sure you understand what power is. It's the rate that you're converting energy. If you have a 60-watt light bulb, what? A 60-watt light bulb? That means you're converting 60 joules of electrical energy every single second to light and probably heat. Okay? We talked about that. We talked about the resistance depends on these factors. This is on your formula sheet. Okay, this is resistivity. So a conductor would have a lower resistivity. An insulator would have a higher resistivity. This is length, and then this is cross-sectional area. So if we were to do something like this, that the length would be this piece, and then that would be the cross-sectional area. A bigger area means a lower resistance. That should make sense. A bigger area means it's easier for the charge to move through. A longer resistor, okay, means a bigger resistance because it's harder for the current to go through something that's longer. It's easier to go through something that's wider, okay? And then this usually depends on temperature, okay? So that's why if you look it up in a table, it'll typically say, at 20 degrees, here's the resistivity. All right, we talked about ohmic versus non-ohmic, which kind of goes along with what we were just talking about. If you graphed this graph up here would be for an ohmic resistor, that as I increase my current, my resistance is staying the same. So that would be an ohmic resistor. So ohmic means that R stays the same. A non-ohmic resistor is one where the resistance changes. Why does the resistance change? Because the resistivity changes. So if I had a light bulb, typically light bulbs, when they get hotter, old incandescent light bulbs anyway, as they get hotter, the resistivity goes up, so that if you had a graph like this for a light bulb, it would look something more like this, because this is getting bigger, so my resistance is getting bigger. So in this case, my slope is getting bigger. If you had a graph that looked like this, well, it would have to be like this, because remember, the slope is 1 over R. Well, if R is getting bigger, that means the slope is getting less. So that would be a non-ohmic resistor. Again, why does that happen? Because this happens. You need to understand the loop rule. So we talked a lot about the loop rule. Okay. Really, if you remember, all the loop rule really is just conservation of energy. And as long as you understand what actually happens in a circuit like this, for example, let's say you were choosing this point to start and you were going to go around that way, because that's the way that current would flow. Remember, we're always talking about conventional current. It goes from positive to negative. Well, the first thing I would encounter is this battery. Well, what does a battery do? Well, a battery is going to add to your potential level. So you would say plus this, and then I would hit this resistor. Well, what does a resistor do? A resistor eats up some of the voltage. It causes you to go from a high potential to a low potential. If I was to color in equal potential lines, this green would be my high equal potential line, and then this red would be my low equal potential line. Okay, but this minus this is going to end up being equal to 0. Why does that happen? Because if you go around, I started on the red, I went up to green, I went back to red, I'm back where I started from. Conservation of energy. So whatever goes in has to come back out. That's really the loop rule. Remember, though, for this class, we had more complicated loop rules. So let's say I had something like this with some batteries in it, and maybe I had another thing here, and maybe another resistor, and I call this battery 1, battery 2, battery 3, resistor 1, resistor 2, resistor 3. So if you wanted to write out a loop rule equation here, you have to pick a point. Okay, remember, this is not a memorized thing. This is an understand thing. So let's pick right here. And then you have to decide. If you don't know, you have to guess, and then you do the math, and then your math is going to tell you. But let's say we guess that it's going to go, the current is going to go around that way. Okay, so if I was to write my loop rule, first thing I encounter is this. Well, if you notice, that's going the right way. So I'm going from negative to positive, so I would increase my voltage, so I have this. Then I encounter this next. Well, that resistor is going to eat up some of the, that would eat up some of the voltage. Then I would encounter this next. Well, that's going the wrong way, so then I would lose that much voltage. I'm encountering this next. That's going to eat up some of the voltage. And then I would encounter this next. That's going to add voltage. And then I encounter that next, or last. And more on this in a little bit, but if you think about current, well, the current is only one path here, so the current has to be the same. So all of these I's are the same. Well, if you plug numbers in and then you solved for I and you got a positive number, that means you guessed right. The current's going around this way. If you plug numbers in and you got a negative I, that just means that the current's going around the other way. Okay? But again, make sure you understand this idea when you're going around a loop, how the orientation of the battery is super important. If you're going with the current or against the current, what that does to, as far as this term, the V equals IR term. So loop rule. Then we talked about the junction rule. So let's talk about the junction rule, which is another kind of basic thing with resistors. And this is really just conservation of charge. When current hits a junction, it splits. You don't lose any current. So for example, this is not a complete circuit, but let's say I have a junction here, and I have wires like this. So this is just a piece of the circuit. So let's say I have current going this way, I have current going this way, I have current going this way, and then I have current going this way. And I said, hey, write an equation with this. Well, here's my junction. You would just go, whatever is coming in equals whatever is coming out. In this case, this is going in, this is going in, this is going in, this is going out. So for this particular problem, it would look like this. Okay, whatever is going in has to equal what's going out. But again, don't memorize it, understand it. Whatever is going in has to be going out. Sometimes, especially in this class, you might have a problem that looks something like this. So let me just make up a question here. So let's say, okay, so let's say I have a circuit that looks something like this. And I'll say this is battery 1, this is battery 2, resistor 1, resistor 2, resistor 3. But then here, if you were to write all the different equations that go with this, let's do the loop rule. Well, actually, we got to figure out which way the current is going first. So let's guess that our current here is flowing this way. Okay, I'll call that I1. Okay, let's guess the current here is flowing this way. I'll call that I2. And then let's guess for this middle part, I don't know which way it's going. Let's guess it's going this way. Okay, and we'll call that I3. So then what you would have to do is, if you were to write let's do our junction rule first. So here's a junction. So if I was to write my junction for that one, I would get I1, that's coming in, and then equals I2 plus I3. That's what's going out. For this one, okay, it would be the same thing. I2 plus I3 equals I1. So my junction rule works. There's my junction rule. Now if I was to write my loop rule. So again, when you're doing your loop, you have to pick a point and then you go around. So if, let's say I pick right here, and I am going to do this bottom loop first. Okay, so I'm going to do that loop. Well, if I do that loop, I would encounter this first. I would encounter this next. So this would be I1 times R1. And then I would encounter this next. And then this would be I3 times R2. That would equal 0. So that would be the loop rule for that one. If I was going to do, let's say I'm going to start here and go around, all the way around, okay? For that loop rule would be, well, I encounter this first, I encounter this next, I encounter this next, which would be plus E2, and then I encounter this next, which would be minus E minus I2 R3 equals 0, and I get back to my starting point, and then I would have one last loop here. So let's say I'm going to do this loop here, and let's say I start right there. That would be plus that, minus, and then now if you look, do you notice how I'm going the wrong way for this one? So then I would have to do it, write it like this, I3 R2 equals 0. Now, you would then have to, you'd have all these equations and you'd have to solve stuff. If your I's came out positive, then you guess, hey, look, it's going, I guessed it's going the right way. If any of the I's come out negative, you would get the other way. But again, make sure that you understand that. Don't memorize it. We did real versus ideal batteries. Real versus ideal batteries. Okay, so for example, if I had this basic circuit again, and if this was a ideal battery, that's what the circuit actually looks like. So that would be an ideal battery. If it was a real battery, in reality, a real battery has this little bit of internal resistance. So it kind of looks like this, where actually this would be my battery if I was to kind of sketch it out. And then a lot of times it would be like, hey, you know what? If you just have your battery and you hook up, it's not part of your circuit, and you hook up a voltmeter across there, this voltmeter would tell you your ideal voltage, because there's no current there. So really it's just the voltage of this piece, where if you hook up a voltmeter here, okay, this volt reading would be less than that volt reading. Why? Because this little internal resistor is eating up some of that voltage. Well, then if you found your potential difference here and here, you know, if this was, let's say this is 6.4 volts and this is only 5.9 volts, that means that this guy is eating 0.5 volts. Well, if you know the current and what the voltage across there, you could find the internal resistance. That's one way you could do that. But hopefully that makes sense. If I was to write my loop rule for this equation, for this circuit, let's say I start here and I go around clockwise. Well, I encounter this first, then I encounter my internal resistance, then I encounter my other resistor, and then I get back to my starting point. Now, it all depends on what the question is asking you to do. If the question is asking you to, you know, let's say you had a graph that was like this, V and I. Well, then, you know, hopefully you realize it would be linear. But if you were to do this one, okay, that, all right, well, let's get it in terms of y equals mx plus b. Well, your y would be this, so if I get this by itself, and then I would get I times this, if you look, in this particular case, that would be my slope, okay? Is it always going to be like that? No. What if you had a graph that was something like this, where it said, hey, I want to graph 1 over I versus R. Well, then I need to solve this for 1 over I. So I want y equals mx plus b. Well, if you look, I almost have 1 over I. I'm going to bring this over here, and I get 1 over I equals R plus R over this over this. Now, if you look, okay, this piece, the 1 over this, would be my slope. This piece would be my y-intercept, okay? But make sure you understand it. Don't memorize it, okay? And then last with circuits, we had series versus parallel, okay? So if I have a series circuit, that let's say my series circuit looks something like this, and I have a parallel circuit that looks something like this, okay? Let's say I add another resistor in series, okay? Here's what I absolutely don't want you to do. I don't want you to try to memorize all this stuff, okay? I want you to understand the basic rules and apply it. So if I had, let's say I had another resistor in parallel, okay, that a memorizer goes, oh, in a series circuit, current's the same everywhere. An understander goes, oh, well, current comes out and goes here and then goes here and goes there, goes there. Well, there is no junction, therefore the current everywhere has to be the same. You understand it. You know, where with this circuit, hey, the current comes out, it gets to here and it splits. It goes, some goes this way, some goes this way. Well, that means the total equals this plus this. Okay? Is it going to split equally? Only if the resistance is the same. So again, understand, don't memorize it. That as you add more resistors in a series circuit, your total resistance goes up. Because if you look, hey, look, this path here has more resistance in it than this path does. So if you look on your formula sheet, this is there. Okay. And it's just saying that, hey, the total resistance for a series circuit is you add them up. Where in a parallel circuit, if you take a look, I have added more paths. If I have more paths, it's easier for the current to get around. So if you look on a parallel circuit, that's why it is written like this on your formula sheet, okay? If you think about voltage, okay, here is high voltage. Here is the low voltage. Do you see battery is going purple to green, purple to green, purple to green? Therefore, the voltage everywhere in a parallel circuit is going to be the same for a given circuit. Okay, so again, you're not going to memorize, you're going to understand it, you're going to have it make sense. In fact, we could also relate it to this equation. You know, these two different things. This is adding a bigger length. If I have a bigger L, my R is bigger, hence resistance adds up. This, if you look, it's like adding a bigger area. If that's bigger, my resistance goes down, hence you have this here. Okay? So again, just be careful, don't memorize, understand. You know, in this circuit, if you add a resistor, you go from here to here, your total current goes down. The current in this circuit is the same, but this current would have less than this. Going from here to here, your total current would go up. Okay? Why? Because there's no more paths, so that you have to have more current to fill up those paths. And then last is make sure you could do combo problems where you have something like maybe like this. Okay, and then make sure you could solve these problems. Remember, this is where you would, hey, look, those two are in series, and then you'd redraw your circuit, and then you would keep redrawing your circuit, and you could solve for stuff. But make sure you are understanding, not memorizing. For example, let's say, hey, you had this circuit, and then the question asks, what would happen if you added another resistor like this? The memorizer would say, oh, well, I added a resistor in parallel. In parallel, the voltage is the same. But it's not going to be the same. The voltage from here to here wouldn't be the same as if that resistor isn't there. Why? Because when I add a resistor in parallel, the total resistance is going down, which means my total current is going up, which means the voltage for this one is going up, which means my voltage from here to here would have to go down. So again, don't memorize things. Make sure you understand it. But all right, I'm going to pause there. That is about resistors. Okay. Bye, kids.